Welcome back. My name is Dominic Clevey. I teach at Central Washington University. Our lesson today is on exponential growth and decay. We've learned a lot in these past few lessons about exponential functions and about logarithmic functions. We've learned that they undo each other in interesting and important ways. We haven't talked a lot about why we care so much about exponential functions in the first place. What do we do with exponential functions? Why do we use them? And what sort of problems can we solve? These are the questions that we'll be focusing on today. Exponential growth formulas are used for the following. This is the formula that you use. The formula we use if, and I'm going to write something that's going to sound sort of math-y at first, but if the growth rate is proportional to the current value. And this could be true for anything. If the growth rate of something is equal to or proportional to its current value, we end up with an exponential function, an exponential growth function. Examples of this are easy to find. Your bank account makes interest. The amount of interest depends on how much is in your bank account. If you have twice as much money, you make twice as much interest. If you have 10 times as much money, first of all, you're very lucky. Second of all, you make 10 times as much interest. It's proportional. The growth rate of human populations usually follows this rule. If you have a country or a state or a town with 10 times more people, there will probably be about, on average, 10 times more birds there. Rates of change that are proportional to current values are very common. And in all cases, to analyze the situation, to solve problems using these, we use exponential growth formulas. And there's really only one exponential growth formula. Formula looks like this. We usually write n of t equals n sub 0 times e to the kt. If we do this, n of t is the number, and you can think of this as the number of people, the number of animals in a forest, the number of dollars in your bank account. This is the number at time t. N0 is the initial number, the starting number. How many you had when you started counting time. K is the growth rate. You'll know, of course, that not everything that grows at the same rate. Even if the two populations are equal, they might not be growing at the same rate. Some people's bank accounts pay higher interest, some countries have a higher birth rate. K lets us capture this different amount in a meaningful way, and T happily stands for, T almost always stands for, T stands for time. This one equation, the current value of n of t is n0 times e to the kt, is the one equation we'll be using over and over again today, the one equation we'll be using to solve problems. And let's look at the kind of problem that we can solve with exponential growth formulas. Almost every book, almost every lecture on the subject starts with bacteria. Bacteria are really good at growing exponentially. The colonies are so big and they're so, frankly, stupid that they can't decide anything. They follow basic laws of biology, basic laws of physics, and this is what they do. Let's assume we have a population of a bacteria colony. We can count the number of bacteria, and this number is growing exponentially, which again is usually the case. When we start the experiment in the lab, there are 1,000 bacteria. 2 hours later, there are 1,500 bacteria. From just this information, I would like to ask a lot of questions. We might ask, for example, how many bacteria there were after just 1 hour. Maybe this was your lab experiment. Maybe you were supposed to count them, and maybe at 1 hour you forgot. You only got the number at 2 hours. Can you work it out? Can we figure out what you missed? How about this? At what time does the population reach 4,000? This is another question that we can answer. We can do almost anything with these once we have these basic starting numbers and once we start to use our equation. And let's think about how to do that. In fact, to do those we have to do something first. In fact, this something is almost always going to be something that we start with exponential growth problems, and we need to find the growth rate. So step one will always be find k. And let's even make that our first challenge explicitly. Let's see if we can figure out what k is. Well, you remember our equation, n of t equals n0 times e to the kt. We know the initial number, we were given that, that's 1,000. Of course, we know the value of e, it's always the same. We know time, and we know the number at that time. At 2 hours, we know how many there are. Remember, if I write n of 2, that really means the number of bacteria at 2 hours, and so I already, just looking at the information I have, know everything except k. This suggests this problem might not be too hard to solve. Let's remind ourselves once again of the equation. N of t equals n0 times e to the kt. 2 is the time that I'm dealing with, the time at 2 hours, the population at 2 hours. N of 2 then should be my initial population, 1,000 times e to the k times 2. And we know what n of 2 is. I know what the population is after 2 hours. I already know it to be 1,500. So 1,500 is 1,000 times e to the 2k. Now all we have to do is solve. If I divide both sides, I should get 1.5 equals e to the 2k. I want to get k by itself, so take the natural log of both sides. The natural log of 1.5 is 2k, and therefore k is equal to the natural log of 1.5 divided by 2. Now I don't have my calculator with me today, I can't tell you exactly what this is with a decimal, but it shouldn't be too hard for us to figure out about what this is equal to. I know that 1.5 squared is 2.25, so that's not enough to get us up to e. This is probably about 1/2 0.5. I'm going to guess this is about 0.28. We can check that later if we need it. In fact, let's check this now. I'm a little worried about this. I'm going to go over to my computer-based calculator. And you should be doing the same thing. Pull out your calculators if you haven't done this yet. Let's figure out what the natural log of 1.5 divided by 2 is. I'm fairly certain I can simply type this into my search window. The natural log of 1.5 divided by 2. And I was not particularly close. The answer is closer to 0.20. Of course, is why we should always use calculators. And now my calculator has magically appeared in front of me. Thank you. Thank you. We can move on. About 0.2 is the answer here. In fact, we can call this 0.203 if we want to keep 3 decimal places. 0.203 is the growth rate. And in fact, this has a very distinct meaning. It's not a magic number. Growth rate is not some sort of mysterious quantity. What this means is the population growth rate is 20%. It's 20.3%. Over any given hour, about 20.3% of the population will reproduce. Now, it's not exactly that, because every time the population changes, the rate of growth changes too. But we can think about this as a good first approximation. This is mostly what it means. Every hour the population goes up by about 20.3%. We found that failure. Now I want to do it, I said, to find more useful things. Now that I know k is about 0.203, what can we do with that? Well, let's ask the next question. The next question was something like, how many bacteria were there? How many bacteria were there after 1 hour? This is the trick that we use if we want to fill in our lab notebooks. And we forgot to take our data. Of course, none of you would do that. Never cheat on your lab notebook. Never do the calculation and say you actually measured it. But if you were that kind of person, this is what you could do. How many bacteria were there after 1 hour? And remember what we have now. We have our equation. Our equation n of t is now good for any time t. At any time t, we can figure out how many there are. There are always the initial number times e to the kt. I know what k is now. It's 0.203 times t. I also know what the initial population is. I know it's 1,000. 1,000 times e to the 0.203 t. And immediately we see how powerful these methods are. How many bacteria were there after 1 hour? After 4 hours? After 13.685 hours? Any t you want, we simply plug it into this equation and find what we need. After 1 hour, I should have n of 1. And n of 1 here is simply going to be 1,000 times e to the, well, 0.203 times 1 is fairly easy to find. We already know that that's 0.203. E to the 0.203. And again, I recommend you do this with me. We plug this directly into our calculators and find it's about equal to 1,225 bacteria. Take a moment and see if this matches with what you thought. If the initial population was 1,000, if it took 2 hours to go up to 1,500, what do you think it was halfway through? After just 1 hour, what should it be? And if you had to guess before we worked it out, mightn't you have said 1,250? after half the time, half the bacteria will have come. It turns out not to quite work like that. That would be true if the population grew with a straight line, if population growth were a linear function, but it's not. Of course, the whole reason we have a section on exponential growth is it's not linear. The growth happens faster and faster over time. This means the growth in the last hour is always bigger than the growth of any previous hour. In the first hour, we gain 225 bacteria. In the second hour, we'll gain 275 bacteria, because these new bacteria will continue to reproduce themselves. What else could we ask? Perhaps when the population reaches 4,000, our petri dish is full. I want to know when that's going to happen, so let's ask that. When will the population reach 4,000? I have my equation. I know how to find the population any time t. And I know what I want the number to be. Remember, n of t is the number at time t, and I want that number to be 4,000. So 4,000 is equal to 1,000 times e to the 0.203 times some t. And now I just need to figure out what that t is. This doesn't look too hard. If I divide both sides by 1,000, I get 4 equals e to the 0.203 t. I want to solve for t, so I'm going to have to take the natural log of both sides. The natural log of 4 then is equal to 0.203 t. This means if I divide by 0.203, I should have my answer. Let's see, t is therefore the natural log of 4 divided by 0.203, which is about equal to 6.83. And remember what we're talking about, time is measured in hours. This is what we're looking at in the problem. So after about 6.83 hours, after about 6 hours, 50 minutes or so, the population will reach 4,000. Isn't it amazing what we can do? Do take a moment and try to be impressed. We have only 2 data points. We know how many bacteria there were originally. We know how many there were after 2 hours, and that's all we know. And from that, we can now answer any question. We can now say exactly how many there will be at any time. We can say at exactly what time the population will reach any number. This equation is a powerful, wonderful thing. We should be happy that we can use it. What else can we do with this? Well, let's ask a question about this. If you have something that's growing exponentially, maybe it's bacteria, but maybe it's much more interesting if it's our bank account. How long does it take to double? All of us would like our bank accounts to double. We'd all like them to double many times if we could. How long will it take? And let's ask that question. Let's say we invest $1,000